So in this lecture, I am going to take a complex example, or you can say lengthy example, and we will see step-by-step explanation how to convert a relation which is in first normal form to BCNF, right? Already I have discussed from first to second, from second to third, right? But in this video, I'm going to combine all the steps, means from first to BCNF, how we are going to convert this relation. So this is the relation and these are the functional dependencies given in this relation, right? And this relation is in first normal form. If you want to check out, obviously we need to find out the candidate key for this. First step is this one, because I have already discussed many videos, many previous videos, right? So how can you check in this is in first normal form? Obviously we'll find out first of all the candidate keys, and then we'll check if there is any partial dependency. Then this is not in second normal form, and that is why it is in first normal form. By default, the relation which is written something like this is we consider that it is in first normal form, right? So now find out the candidate key. First of all, how to find out that also I have already discussed. How to find out candidate keys from a given relation in my previous videos. I provided the link of the complete DBMS playlist in the description box. You can check out there, right? So now take all the attributes of the relation and find out the closure. Obviously it will find out all the attributes, right? Now try to discard the attributes using functional dependencies, right? A can drive BD, so if you have A, I can discard B and D, right? See, B can drive C, means if you have B, you can drive C. Now obviously if you have A, I can drive B, right? And if I have B, then I can drive C, so I can discard C as well. Using E, I can drive E and F, so if you have E, you can discard F and G, right? Now if you have A and E, so you can drive H, so you can discard H because I have A and E. So the remaining attributes are only A and E. Find out the closure. See, using A, I can drive A, E definitely. Using A, I can drive BD. Using B, I can drive C. Using E, I can drive F, G, and I can drive H. All the attributes I can drive. So A is what? You can say it is a super key. We cannot discard any more elements, any more attributes from here. So this is super key. Now, proper subset is A and E. Obviously, no proper subset would be super key because A closure would only contain A, then BD, then we can drive C, right? Not all the attribute. E closure can contain E, F and G only, right? So no, this is neither this is super key or no, this is super key. So that is why we can say that A, E is our candidate key, right? Now prime attributes are A and E. Fine. Find out more candidate keys are available or not. If prime attributes are available on the right hand side of any functional dependencies, means there are still more candidate keys, but A and E are not on the right hand side, so there is only one candidate key, that is A. Fine. Now find out which functional dependency is creating problem. It means which functional dependency is partial dependency, right? See, A can drive BD. Partial dependency means the proper subset of this candidate key drives non-prime attribute, then that is partial dependency. A is partial subset and BD, yeah, this is non-prime attribute because prime attributes are only A and E. So this is partial dependency, right? Is B proper subset of this one? No. So obviously this cannot be a partial dependency. E is proper subset of this one? Yes. FG are non-prime attribute? Yes. So this is partial dependency. A is proper subset of candidate key? No. A is itself a candidate key, or you can say super key. So this is not partial dependency. Means these two functional dependencies are creating problem. Because of these two, this relation is not in second normal form, it is in first normal form. Now we have identified the dependencies which are creating problem. So next step is what? Take out this one, this functional dependency, and find out A closure. A closure would be this one, A, B, C, D, right? Using these I'll find out. Now put all these attributes in one relation, right? Find out E closure. E closure would be E, F, G. Put all these attributes in another relation, right? And put all the remaining attributes in a third relation. Remaining attribute is H only, right? But we cannot put only one attribute in this. So now what you have to do, see, now there should be something common, right? Because in this and this there is no common, in this and this also no common. So when you will join, there should be something common to be a lossless joint decomposition, right? If nothing is common between the relation, then this is lossy joint decomposition, right? And we want lossless joint decomposition and dependency preserving. So if we join this one and this one, so what should we put common here? See, the common attribute should be super key, or you can say candidate key of at least one subrelation, right? To be that decomposition a lossless joint decomposition, right? So suppose I put A common here. Obviously A is candidate key for this one because using A I can drive B, C, D, all the attributes. So it's better to put A common. You can put B common, either C or D, you can put these things common and you can check out, right? Those would be lossy joint decomposition, right? Now, between this and this, what should be the common attribute? It's better to put what? E common, because E is what? Candidate key for this subrelation, or you can say super key for this subrelation, because E can drive F and G, all the attribute of this subrelation, right? So now this is our third relation, or in simple terms you can say in one relation we always put the candidate key. See, remaining attribute is H, and obviously the candidate key is what? A, so we put A here. So that thing also you can consider, or you can apply the logic which I am telling here in this video, right? So now we need to check, this is lossless joint decomposition, right? But we need to check the highest normal form for this also, and this also, because we are supposed to convert it into BCNF, right? Now check it is converted into BCNF or not, or it is still in first NF or in second NF or third NF, we can't say. So for that we need to find out the functional dependencies and candidate keys, right? So functional dependency for this relation would be how to find out functional dependencies. That video I have already discussed in detail. I'll provide the link of that video particularly in the side button, you can check out there. Here I'm just writing the functional dependencies, right? So the functional dependency for this one would be, here A can drive B, C, D, because when you find out A closer, you will get this one, and A to A is trivial, and B, C, D, right? When you will find out B closer, then you will get B to C, this functional dependency, right? How to find out? You have to consider this functional dependency, right? Now if you find out C closer, then what would be the case? C closer would be C only, because C, using C I cannot drive anything, so this is trivial, so we are not going to take it. D closer also, you can only get D, nothing else, so this is also trivial, we are not going to take it, right? Now A can drive all the attributes, so no need to check with AB, AC and AD like this, because that would be duplicate, right? And B can drive C, C and D are driving nothing, so no need to check BC, BD and CD, right? You will not get anything. You will check, you can, if you want to check out, you can check out, right? So you will find out only these two functional dependencies here, right? Now in R2, functional dependency would be, if you find out E closer, then F, G would be there. If you find out F closer, nothing you will get. F to F trivial would be there. G closer, nothing you will get using these functional dependency, right? So there is only one functional dependency, right? E can drive all the attributes, so no need to check EF closer and EG closer, because obviously that would be a duplicate. And if you find out FG, then that also would be trivial, only FG you can drive using FG. FG closer would be FG only, right? So no need to take. There is only one functional dependency here. Now here, functional dependency would be, see if you find out H closer, you will get only H, trivial. If you find out A closer, then you will get this one. But A to A is trivial, B, C, D are not part of this one. So no need to take this one, we are not going to take. E closer would be EFG, E to E is trivial, FG is not part of this subrelation, so we are not going to take it, right? So now one dependency would be there here, AE. If you find out AE closer, then that would be A, using A I can drive BD, using B I can drive C, using E I can drive F and G, right? Using AE I can drive H, all the attributes. A to AE is trivial. See, D is not part of the subrelation, C is not part of the subrelation, F is no, and G. Only H is part of the subrelation, so AE can drive H, right? Same you can find out AH, same you can find out EH, right? You will get nothing. All the attributes, those you will get in closer that are not part of the subrelation, right? So we are not going to take those functional dependencies. So only one functional dependency would be there in this case, right? Now find out the normal form for this, and this. Same for that you have to find out candidate key. The same process you will apply in each subrelations, right? I'm not going to apply again because we have already discussed one time. So when you apply the same process, then the candidate key for the subrelation would be A. From here only you can check A can drive all the attributes, right? So candidate key would be one, candidate key is A, and A is not on the right hand side, so there is only one candidate key. Here the candidate key would be only E, and here the candidate key would be AE. Now see, is this partial dependency? No. Is this partial dependency? No. Means this is in second NF, definitely. But is it in third NF? See, check. For 3NF, two conditions are there. One of those two conditions should be satisfied. Either left hand side is super key or right hand side is prime attribute. Is left hand side super key? Yes. So this is not transitive dependency, right? Is left hand side super key? No. Is right hand side prime attribute? No, because prime attribute is only one A. So this is transitive dependency. So this relation is not in third normal form, it is in second normal form, R1. Check for this one. E, the left hand side is what? Only one dependency is there, and the E is what? Candidate key, or you can say super key, right? So if the left hand side is super key of the functional dependencies, of all the functional dependencies, then that relation is in BCNF. That rule we already discussed, right? So this is in BCNF. This one, left hand side is what? Super key, or you can say candidate, obviously candidate key is super key also, right? So this is also in BCNF. But this is in second NF, right? So it's not like that we have got two BCNF, so it is in BCNF now. No, it is still in second normal form because the lowest one we are going to choose, right? That is second normal form. Now you have to convert this subrelation only into third NF or BCNF. This we have already got two subrelations, right? Now we are going to work on this R1 only. Now here, which functional dependency is creating a problem for third NF? This one only, because this is not creating a problem. This is not transitive dependency, this is transitive dependency. So now take B closer. Now, see, we are not going to consider now this functional dependency, because now we are decomposing this relation R1, and we have already got the functional dependency set for this subrelation. So now we will consider this one to find out B closer. So B closer would be B, and using B I can drive C only, BC. So one subrelation would be suppose R11, that is BC, and remaining would be in second subrelation, that is A and D. Now we have to put something common, right? To get a lossless joint decomposition, common should be at least super key of one subrelation. As we know, B can drive C, so B would be definitely super key, or you can say candidate key for this subrelation. So better to put B common, right? Now find out functional dependencies, and then find out that this is or this is in BCNF or not, or still in third NF or still in second NF. This is having only two attributes, so this is definitely in BCNF, right? Check for this one. Find out functional dependencies first. F12 set would be, if you find out A closer, you will get A can drive BCD, means B D, because C is not part of this subrelation, right? If you find out D closer, nothing you will get, trivial functional dependency you will get. If you find out B closer, then you will get B and C. B to B is trivial and C is not part of the subrelation, so we are going to take only this one, right? because A can drive all the attributes, so no need to check AD and AB closure, right? And if you want to check BD closure, then you will get what? B, D and C only. So BD is trivial, C is not part of this one, so we are not going to take that functional dependency also, right? So there is only one functional dependency. Now if you find out the candidate key, then candidate key you will get, that would be A only, right? Now if you check left hand side of this functional dependency is A, that is candidate key, or you can say super key. So this is definitely in BCNF. So now this is in BCNF, right? Now finally we have converted it into BCNF, right? Because, and now how many subrelations are there? 1, 2, 3 and 4. We are not going to consider this because we have decomposed it into this one to convert it into BCNF, because it was in second NF, right? So 4 subrelations are there, this one, this one, this one and this one. And if you are asked how many subrelations would be required to convert this into BCNF, then your answer would be 4 subrelations would be required, these 4 subrelations, right? This is the step-by-step explanation how we are going to convert a relation which is in first NF to BCNF, right? So that's it for today. Now I'll see you in the next video. Till then, bye-bye. Take care.